Okay, good evening everybody. I hope everyone's having a wonderful day. So today I'm going to be talking about hashing. Now, before that, I just need to remind you that in the previous lecture, I had talked about dictionaries. So there's this concept of a dictionary ADT. And remember in this, there are three fundamental operations that we're interested in, where we maintain a collection of pairs where they have a record and some data or value. And these three operations are get, which is like finding that record and getting its value. We had put, where we want to insert the record in, but it's important that we maintain that the dictionary always has a unique set of records where each one of the keys is unique. The data or value doesn't matter when it comes to multiplicities or duplicates. It's just that the keys all have to be unique in the dictionary. So we always have to keep that in mind when we create or maintain the dictionaries. We have to make sure that we don't introduce new records in through our put operation that have duplicate keys. And these keys, as a reminder, are unique so that we can index and get those records and their data. And then lastly, there's the remove operation. So I give you a key and I want to delete the record from the dictionary and return its value. So in these cases, whenever I fail to find it, with the exception of get, so if I get a duplicate, for example, so if I fail to perform the operation, an error happens. So just keep that in mind. So that's what I mentioned about last day. So I want to talk about one other way we can implement a dictionary. So as I mentioned in my previous lecture, we're going to focus a lot on implementing dictionaries. Why? Because dictionaries are one of these more fundamental data structures. You've seen plenty in this course up to this point. The dictionary is just one of these. So I'm going to show you an interesting way of approaching this, probably this lecture or potentially the next lecture too, is using the idea of a hash table and the idea of hashing. So what does that mean? So I've talked about a couple different ways to implement a dictionary at this point. So what's the strategy? So remember we talked about how I can use for example, a linked list. I could use a sorted array, for example. But what's my strategy here? The goal I'm going to have here is I'm going to use some memory to allow me to speed up some operations under certain assumptions. So I want to give you kind of like an overall game plan of what we're going to do and how hashing is going to work. And then what we're going to do is we're going to walk through kind of the principles behind hashing. And then we're going to ultimately see how we can design and develop our own hash table. So before anything, I just want to give you the general setup. So remember, my goal is to maintain a dictionary in this case, and I must stress that the dictionary is just a vein or a vessel for me to show you these different data structures. So you can use them in different contexts. The dictionary is a very useful one in this case. So what's a hash table? It's simply, you can think of it as just an array where I'm going to have it where it's going to store records. You can think of it like a lookup table. So I'm going to have a table or array that's going to be of size capital M. That's going to be what I'm going to assume is always going to be the table size is capital M. And I'm always going to assume, for the sake of this discussion, that capital M is always going to be greater than or equal to the number of elements I'm going to place, or in our case records, number of records I'm going to place into the table. However, it most certainly will not be the case, as we're going to see, where we're going to start running into problems sometimes. So sometimes I can make this assumption, sometimes I'll show you some broader ones we can make. At first, you're going to see that this constraint isn't really going to be much of an issue for us at all. So here's the idea. Suppose I have a bunch of records I would like to put into the hash table. So suppose that one pair is K1, V1, next one's K2, V2, and the next one's K3, V3, and the last one is KN, VN. So all of these records I would like to place into this table. Now, you might say, Dan, why do we want to store this in some array? Surely we have some ways of implementing that, right? With like a sorted array, for example. Now, here's the idea. Now, first, just take me at my word, and I'm going to try to give some substance to this as we go along. Here's the idea. So suppose that I use this key. So each one of these records has a key. What I would like to do is I would like to feed this key to something called a hash function that tells me a location to place the record. So if I can ensure that this hash function, to compute this, takes big O of 1 time, if I give you a record and I compute its location, I place it in the table somewhere in big O of 1, which is constant time. So if I'm able to accomplish this, I can just simply tell you where that record is going to go. So when I do an insertion, or if I want to do a search, I just simply use the hash function to tell me where it is in this table. So the general gist of this is I use this to tell me where I should place this. For example, K1, I give it to this hash function, for example. It may place it in position 2 of the table. It'll tell me, hey, look, that's where you're going to place it. And it's all dependent on the key. So the keys will be used to do this hashing process. Yep, that's okay. I can walk through it again. So remember, I'm going to use an array that I'm going to refer to as a hash table. And suppose I have n records I would like to put into this table. So here's the idea. I have all of these records. I'm going to try to insert them into this table or allow it so that I can easily find it using this hash function. So I'm going to define what this is in a little bit. So don't worry, I'm just kind of keeping things high level at this point. So suppose I have each one of my keys for my records. I'm going to use this key for this so-called hash function. And this hash function ideally will compute in big O of 1 time, or in constant time, a location for me to place the record in my table. And the idea is if I ever want to come back to that location in the table, I can just use this hash function to tell me where it is. And now, here's the thing. Assuming everything I've just told you is just straight up legit, if I were to suppose I wanted to know where the record with key K1 is, does anybody have any ideas how I can find it? Now, I must stress, I'm not trying to search through the array. I just want to put this key into the hash function, and it should be able to tell me where it is, right? That's it. So if you notice very quickly that if I'm able to quickly figure out where it is, or where I need to place the element or record in my table, then I could do this fairly quickly. So in fact, under the assumptions that I'm going to be using today, you've seen how we talked about some of these operations for simpler implementations that we had, how there's sort of a trade-off where my insertions and the removals seem to have this balancing effect going on. So I'm going to show you one technique we can use to speed up these operations using hashing. So I'm using this extra space to store this along with using this hash function to tell me where these records are going to go. So here's what I'm going to try to accomplish. So remember, I have get, I have put, and I have remove. So these are my 3 primary dictionary operations. So remember, whenever I want to use the hash function, I just use this key, I feed that to the hash function, it tells me where it goes. Same idea with put. This is kind of the high-level view of what we're going to be trying to accomplish. But here's the idea. If under the assumptions I'm able to give you here, and at least it'll be for practical speaking, it'll be something that we'll try to match up with, we can try to obtain big O of 1 average running times. So under some assumptions we're going to make, I'm going to try to show you that you can actually achieve all 3 of these operations in big O of 1 average time. So in the average case, you'll end up with big O of 1, which is very nice, right? It's not a whole linear, it's going to be something that's going to operate quite quickly on average. So there's going to be some assumptions that come with this baggage, just to be very clear. There's a couple of assumptions we make about the design of our hash table and some statistical ones we will assume. So this is the general idea. We're going to be figuring out how to use this hashing idea that I just described to you. This is the idea of hashing. So I'm going to try to accomplish this under specific assumptions. And I must stress this technique can be used not just necessarily for dictionaries. You can use this for all sorts of different settings. So I'm just showing it to you just to give you a flavor for what is possible with hashing. So I want to give you an example just to kind of give you a flavor for this. So in the hash table, H, in the hash table comma H, the hash function over there, must give a position for every key, or I'll call it ID, key or ID. It will be some piece of information that you're going to be taking along with the data to place it into the table. So I'm going to give you an example of an application where you might find this quite appropriate. Because remember, I talked about dictionaries before, so I want to give you an example. Consider the set of all possible student IDs at U of Regina. So I'm going to consider all possible student IDs for all of, so I'm going to take I want to know all of the student IDs. So I'm going to just say that, and each of them are going to have digits. Each has digits. We'll go D8, D7, D6, D5, all the way down to D0. Because it's 9 digits, right? So, just to give you a picture of what I'm going to try to accomplish, so I'm just going to draw a picture here. So one thing you'll notice very quickly is that if I wanted to know how many of these are possible, we might be in for a fun time, right? We might be in for a very fun time. Does anybody have any idea of how many possible student numbers there are, or student IDs there are, given this setup? So there's a lot of them. There's a lot of them. So keep in mind that each digit has 10 possible values, right? Roughly, right? 10 possible values. So if you think about it from a counting standpoint, it would be, okay, so I have digits from, I can put it in the first digit, I could put 0, 1, 2, 3, 4, all the way up to 9, right? There are 10 possible choices for the first digit. Then I can do 10 possible ways for the second digit. Then I can do 10 possible ways for the third digit, and so on for all of the digits. And there are 9 of them. So any ideas of how many possible keys there can be? So there are, how many do we have at night? So think of, so very close, very close. I'm seeing a couple really good guesses. So think about it. Each time I have a digit, I have 10, I can make 10 options. So very, very close. I'm seeing like 90 factorial, I'm seeing 9 to the 10, I'm seeing 10 to the 10. I see 10 to the 9. That's the one I'm looking for. Why? Because think about it. Each one of my digits, so remember I have 1, 2, 3, 4, 5, 6, 7, 8, 9. And each one of these, I have 10 possible choices, right? A number 0 through 9. So there's this times how many times this can happen, because all of these are independent of each other, right? They're just some digit. There's no relationship they have among each other. So each one of these is 10 times 10 times 10, all the way till I get to the 9th digit. So there are 10 to the 9 total number of possible keys, right? That's a lot, right? Now you might naturally say, Dan, that's a lot. Like even practically speaking, this might be this is a bit big. So and I've told you, I would like to use some memory to speed up my operations, like my get, put, and remove. So I'm going to use this hash table to store these records, but most certainly I'm probably not going to need all 10 to the 9 spots in a table, right? In practice, what I do is I decide the size of my table, and this is something I consider from a practical standpoint, so I have to determine a reasonable size for this table. So suppose that I have, because surely this is much bigger. This is a lot bigger than I probably need for what I'm currently doing. But if I need to make it bigger, I can make it bigger. So suppose that I just use, say, 10,000. Say if I make the table have 10,001 spots in it. So if we think about it, if I give you two IDs, two possible IDs, say if I give you two IDs, I call them ID1 and ID2, and I apply my idea here. Because surely using this, if I made this 10 to the 9 in terms of its size, that's really big. That's a lot of memory to use, right? So what I would like to do is try to find a fair compromise between the speed up I would like to get from using the memory, but also I would like to have it so that I still am storing enough information as needed so that I can have my nice setup with the hash function. So think about it. If I have less than 10 to the 9 possible keys, sorry, I have less than 10 to the 9 here. There's 10,001 entries here, right? Does anybody have any speculations? Am I going to be able to fit 10 to the 9 possible keys in this table? Are they all going to be able to fit in there? No, right? It's like magnitudes off. So when you naturally have it where we apply our idea, so I give it some ID. Suppose I put in ID1. It gives me some location, and it tells me, oh, okay, I'm going to put it here. So whatever record has ID1, I place it there. So what if something else comes along, say, for example, ID2? Suppose that there's another ID that when I give the ID to the hash function, it tells me to put it right there. Is that going to be a problem for us? Well, like which one should stay and which one should go? That's a little bit of a problem for us. So this is a standard problem we have to deal with hash functions. So notice that the number of possible keys is much, much larger. It's much larger than the hash table size. So that means that it's going to produce this issue what we're going to run into where two IDs could potentially hash using the hash function, give us the same location. We have a name for this. The hash function will produce collisions. So that's what we refer to when we talk about a collision. It's just when you have two records that have, say, two, and keep in mind, these don't have to be the same ID either. So just to be very clear, it's very possible for this to happen even if these two IDs are distinct or different from each other. So you're going to see that as I'm trying to adapt this idea, we're going to run into this issue of the hash function mapping some ID from its hash function to the same location. And this is what this causes collisions, and I would like to be able to resolve these. This is going to be an important aspect of dealing with our hashing. So just be aware that just because these two aren't the same value, they can still hash to the exact same location. So we're going to see very quickly that I would like to make effective use of the hash table to resolve these collisions. So you're going to find that most of the discussion we're going to have, because you know how to implement an array, right, is to give algorithms for how to resolve collisions and do so efficiently. So there's that aspect. There's also this aspect of why did I pick 10,000 or other things like that. We're going to talk about that because when I have my three operations, get, put, and remove, I would like to achieve a speed up possible through hashing. And keep in mind that's in the average case. We're going to see in the worst case, it's still going to have problems quite similar to the ones we had for our other implementations. So is everybody kind of excited? So this is something a little bit different. There's some things we're going to have to consider very carefully here. So how are H key? So remember, H of the key, that's the hash function. Then we have our three operations, get, put, and remove. These are our dictionary operations. So they're two separate things. So just like when I talked the last lecture about how to implement get, put, and remove, this is just going to be how we're going to implement those three operations. Just like when we talked about stack. Exactly. Very well put. So I want to talk about these considerations just so we have an idea of kind of the big game plan. So I want to make sure I give us a very clear roadmap for how we're going to adapt this idea of hashing. And you're going to see that we can still get some rather effective practical ability from this hashing if we take all three of these into account carefully. So I'm going to be showing you about each one of these. So we're going to get a flavor for how to, for example, deal with all of the things I highlighted here. So these are some key design issues that we're going to have to consider, and I will consider all three of these. Some of these are practical, some of these are heavily theoretic. So both of these, you're going to find sometimes I'm going to bring out numbers just to give you an idea of certain empirical results that actually work quite well in practice. Other ones are going to be heavily theoretic. So sometimes it's necessary, sometimes they're going to be more practical or optional. So anyways, there's a few of them that I want to highlight here. For example, you notice how I picked 10,001 for the size over there? That could have easily just been a consideration I made from a practical standpoint where I tried various sizes for the hash table and seen which one led to the best performance. That's one thing that always can happen. But there's also some times where we have to seriously consider the size of the table. So what's the ideal size for a table? We're going to try to address this question. The other one is the selection of the hash function. That seems to play a very important role in how all this hashing works. Because, like I said, you're kind of taking my word for it that this hash function does this thing where it takes in a key and it tells us a location to place it in the table. And we have this issue involving collisions that we have to think about. So we're going to talk about how to pick a hash function. And keep in mind, the goal here is to make a really fast and efficient one. There's other times where you can use hashing where the computing this might take a little longer and it might be able to get us some better outcomes at the end, but we're going to take a penalty of how long it might take to compute this function. Here where we want really fast functions for computing the locations. And we want to make sure there's very few collisions that happen. But here's the most important one for the assumptions we're going to make to try to achieve that big O of 1 average case time. Is first, we're going to assume that our hash function should be able to spread the keys uniformly across the entire table. Just like if I took a butter knife out and I had a really nice bagel or a nice big slice of bread, maybe like a 3-foot long piece of bread. Okay, it would be much longer than this. It would be more like something like this. Take a very thick, very wide butter knife and spreading it across the table. I would like to spread out that butter across this really long piece of bread. I want to make sure that this hash function, when it assigns locations, it doesn't clump them all together in one spot. It spreads them uniformly across the table. So that every time I make a hash with a given key, its probability of going into a spot is actually more from a probability standpoint related to the number of elements and the size of the table, not just simply it's just going to lump them all in one spot. I want them to spread across. So I'm going to show you an example of one practical way of trying to achieve this. It doesn't necessarily guarantee it, but most certainly it, practically speaking, is effective enough to achieve something like this. Why do we want them to spread out? Because we want to resolve and try to avoid collisions. Because remember my picture over here. So remember my picture I had over here? Where I had it where it's all the way over here. It's all the way over here. I'm over here. Hi guys. I'm over here. So I'm over here. So remember in my hash table, the hash function will assign a location, right? And I would like to make it so that when I have two IDs that are similar to each other, I don't necessarily want them to be right beside each other. I want them to be spread out. So when I have, say, this hash function, I give it a key, it should tell me a location. I want them so that they get spread out as evenly as possible. So that if I have several keys coming in to my hash function, they all don't hash to the same location. Because when I have collisions happen, I have to fix the table somehow. And that will end up being some bottleneck in our process when it at least comes to the algorithms. Is if I can make it so it's simple as just simply, I have my record, I have a key, and I put in my hash function, it tells me a location. If I can ensure there's no collisions that happen, I end up with that nice constant bound because I have no worries about having to fix anything in the table. Is that clear? Yeah, we're going to be moving back over to this board. I just wanted to highlight this one thing. But yeah, so that should, I'm hoping that this will give you some intuition. We want to avoid these collisions. And if we can try to make a nice hash function that spreads out the keys as much as we can when we assign the locations from its hash function, we can avoid many, many collisions from happening. So under this assumption, this is going to be an assumption I'm going to make every case when I discuss the effectiveness of these hash functions. I'll be making the assumption that you've designed one that's able to achieve something approximating that it uniformly spreads the keys across the table when I apply them in the hash function. So this is going to be my technical caveat. So just be very aware that this is an assumption I'm making. Sometimes you can actually just straight up achieve this, but in practice, I'm going to be showing you a very effective way of achieving this. But it's only going to be from a practical standpoint. But most certainly, it's good enough. It should give you this type of behavior. So why do we need the size again? Because we have to assign the table a certain size. Otherwise, we can't put records into the table. Because remember, the table is going to store all our data. Or at least you could think of it as even a stepping stone to get another data structure that you could store a reference to in the table. You can think of the hash table like a lookup table. It makes things a lot easier to visualize, where I have my keys. Each of the keys gives me some way of looking up the data in that location in the table. But yeah, so we have the hash function. The third one is this collision resolution. How are we going to deal with the collisions? Yes, so as I said previously, the hash table would be an array. So in our case, we could just think of it just like an array. That's it. Now keep in mind, you can always stack on top of this some more sophisticated structures, but for us in this discussion, we'll just think of it like an array. But I must stress, as you're going to see, I'm going to come up with different so-called collision resolution schemes that are going to modify this idea. So some of them are literally going to be like an array. Other ones are going to be where I have something that's like an array, where I make some modification to it, where it's going to still have that overall idea where we index into a spot, but I might make some modifications to the data structure to allow it to avoid or resolve these collisions. So keep in mind that the hash table does not have to maintain any special ordering, except for that as long as it abides by maintaining where the locations that we place for collision resolution, as long as they are in the appropriate spots, that's all that really matters. But yeah, so these are the three things we're going to have to take into consideration when we do this. And I'll be giving you algorithms based on different collision resolution schemes for achieving each one of these kind of a consideration. So some of them won't have any consideration like this. Other ones might be able to do a little bit more with this, and other ones will be quite clear that this is kind of the goal. But yeah, so these are kind of the three main things we're going to have to take a look at when we consider each collision resolution scheme and how we design the hash table. But yeah, so anyways, the first thing I need to do is talk about what a hash function is, because I've sort of just glossed over that detail, just kind of giving you the high-level description of what a hash function is. So I'm going to talk about what a hash function is. I'll give you an algorithm that will suffice for computing for our hash function. But please remember that I'm making a technical assumption every time I do my analysis in the average case, that the hash function is going to be sufficiently able to uniformly spread the keys across the table. So let's talk about what a hash function is. So I must stress that the hash function, as the way I described it, it almost sounded like I was just talking about a bunch of numbers that go into a function and they give you a location. This most certainly can be the case, but I must stress that keys can be of any type. At least for our colloquial discussion. So like an integer, they could be integers. They could be a string, for example. They could be a character. Could be an array, for example. So the concept of a key, like in our dictionaries, can be fairly broad. And the same in the case of hash functions, we can make them quite flexible. So let's define what a hash function is together. So a hash function consists of two main parts. But let me define it, and then we'll talk about each piece. So, hash function h, given an input that's a key, is defined in terms of two parts, a function f and a function g. So there's this function g that takes in key, and then what it does is there's another function that takes the whatever is resultant of g for this given key, it applies this function f. So I'm going to define what those things are. So a hash function has two parts. It has two parts. The first one is what we call the hash code. So the hash code. So this is the function g. And this function will always, and it produces an integer. So what will happen is I give it a key, and it'll spit out an integer at me. That's the job of G. That's what the hash code's job is. So to give you a little bit of intuition around the hash code, is I would like to make it so that the outputs of this function can be as large as I can to make sure that they spread across the table, as per my assumptions, at least my goal here. We want the integer to be large to make sure all entries in the table are used. I'll tell you up front, the hash code does most of the work. Often when people define hash functions, they take the two parts together. So this is the first part, it says hash code. So it spits out an integer based on the key. The second one is this so-called compression map. So we have the compression map as the second part. So to get a little bit fancy, it's a function F. So I'm going to use some mapping notation. I'll explain it in a moment because I like to just expose you to things every once in a while. So I feel like just showing you this. So it's a function that takes in an integer. So it takes in an integer as input. And as output, it gives a number within the range of 0 up to m minus 1. Remember, capital M is the size of the table. So just to be very clear what this means, this just says takes an integer. It takes an integer and gives a position in the hash table. So that's what it does. So you can imagine the hash code computes some value. This might be out of the range of the table. So the compression map's job is to wrap everything back inside the table, just to make sure that whatever number that we get out of this hash code, it's all within the confines of the table. Why don't we just use the integer from the hash code as a position in the table? So that's a wonderful question. So this is actually the key role of the compression map. So for example, if I had this, so for example, this is just a little doodle off to the side. Suppose that I have a table of size m, and remember, this just produces an integer, and we would like to make them large enough. So suppose that if I use the hash code and I use this function g, and suppose that it hashes a value, and the value is sitting just outside the array. Suppose it's at position, so the imaginary position m, which doesn't exist in the array. Well, that's possible with the hash code. So what the job of the compression map is just simply to make sure that if I give you a value like this, it tells me where it should be located inside the table. Typically, if it's outside there just like this, you'll typically wrap it around and place it back, say, over here. But yeah, the role of the compression map is just simply to make sure whatever value I get out of this function, because this function might be some completely arbitrary value that might be really, really big, but I know how to compute it. I need some way to make it so it's inside the table, because remember, the goal is to get a location that's going to be inside the table. Is that clear? But yeah, together, what we do is we apply the hash code to get an integer. And then what we do is we use this compression map, which I'll show you an example what I mean by this. It's going to take whatever this number is and it's going to make it so it's some value between 0 and capital M minus 1. So that makes sure it gives us a location. And that's all a hash function is. So I got to talk about the bits and pieces now. So notice I'm going to now go down a little bit lower, and now I'm going to talk about what a hash code is. So now I've given you the definition of a hash code. I would like to talk about designing a hash code. Because remember, all it does is it takes in a key and it produces a value. So I want to show you a couple different ways you could design a hash code. These aren't the only ways, but this is one of the more, I'm going to give you some common pros and cons for designing the hash code. So I'll tell you up front that the next assignment will get you to play around with some of these things. I usually like to give you something you can play a little bit around with this hashing idea. So, let's talk about hash codes. So hash code. So I'm going to first just consider kind of the typical scenario. Oftentimes in dictionaries, for example, you'll have it where the key might actually be a key identifier, which sometimes is sometimes is a string. It might be just a unique number, but often it might be a string. So I'm going to show you first just an idea. If I give you some string, how can I make my hash code? So I want to kind of touch on a couple of small things. So let us consider. So I'm going to pick up something that I'm sure you've seen before. If not, I'm going to remind you of it. let us consider converting a string s into an integer. So you may not have tried this before, where I have a string and my goal is to produce an integer. So that's what we're going to try doing, because very often we have it where the key is actually a string, very often. So I'm going to show you some ways we can convert a string into an integer and some effective ways to do so. So first, does anyone have any ideas of how we could proceed with this? I usually like to throw it out there. So, you know, strings they consist of characters, right? So what can I do with each one of those characters? So I want you to think back to talk about primitive types. Yeah, look at the code, but how do we do that? Yeah, assign each character a number, right? Now, the great thing about how characters work on computers is that they actually do have a numeric value. And we could, yeah, exactly, talking about the ASCII, right? So each one of our characters actually has a value to it, and that's what we could take advantage of. So I'll say we can take each character and convert it using casting, right? I can cast the character to an int, for example. So just to do an example, so just as an example, so suppose I give you a string s and I want to know what the value would be for a position I in the string. So suppose I want position I. Here's what I can do. So the first thing is I have a character. I'm going to give it a name C. I want to just use the @ function for the string. I can use @ to get the character at that position in the string. Then, second thing I could do is I could just have a variable int, and I can of course just simply assign value by just casting the character directly. Now, here's the great part. So it was brought up in the chat here, but I thought it would be used, talking about an integer. Now, here's the interesting thing. If you actually look in the ASCII table, if you ever find yourself curious what I'm talking about, look up ASCII table of characters, and you'll find that for every lowercase letter, uppercase letter, number, any keyboard inputs, they all have special numeric values that have correspondence in base 2, and also in hex, then also in decimal. So all of these, if you want to try this sometime, just try picking out your favorite string and try to print out what its value is using something just like this. And each one of them will have a numeric value. This is something really helpful, especially if you ever find yourself implementing things that have keyboard input and you want to just know what the symbol is. But anyways, I'm going to try to apply some function to get a number. So I'm going to you're going to think of this like my first attempt to design a hash code. So I want to do this with everybody. So here's my first attempt to try to use this idea. Let's do a first attempt. Here's our first attempt. So I'm going to take function g. Remember, that's what my hash code is function g. It's going to take in characters. I'm going to label them backwards like this. So I'm going to say the first character is C with the subscript k minus 2. Sorry, k minus 1. Then I have C k minus 2 all the way down to C1, C0. So this is the input for my function. I give it a string, and it'll output an integer. So what is it going to do? All I'm going to do is I'm going to compute a sum over each one of the characters where I cast it to an integer. So each one I'm just going to cast to an integer. So this is my first attempt. So all that is saying is I'm going to look at each character. You can implement this with just a for loop. So remember, all I'm doing is I'm summing over each one of the characters a value that I get from casting, just like I did here a moment ago. And you can get a number from doing this, right? Does everybody understand how this works? I would just have a for loop, for example, to compute that sum. I just go through each one of the positions, and then I cast the character to its integer value, and I just add it to a running total. So any questions about my first attempt here? So this is just my first attempt. So I'm just taking each one of the characters, I cast it to an integer, I just add it up. I add up each one of the values. So you might ask, Dan, is this a good hash code or not? Now, I want to give you some convincing that this isn't actually a very good hash code. There's actually some very good reasons why, but I want to kind of bounce off ideas with you. So I want you to think about how we computed this. So when I did this, I just took each one of the characters, converted to its integer value, then I added it to a total. So there's really kind of two things you got to take into consideration at least when I do this. Yeah, that's exactly what I was thinking about. That's a wonderful suggestion. So it says, so the chat say, sorry, I'm getting very excited here. I'm really happy when students point this stuff out. So couldn't different combinations of characters add up to the same total? That is absolutely correct. That is the biggest problem with this hash code. So let me just talk about that. So this is not a good hash code because there's kind of two main points. The first one, maybe I'll start off with the most given one that I could think of. Now suppose that my table is just really, really big. Like say it was 10,000, like 10,001. You can make these things quite big like this, and they work quite effectively if you have the space. Suppose I only have like a string of, say, 3 characters or versus 5 characters. Like I may not actually get a number that's big enough to get me all the way over to, say, the end of this table, right? So the values I might get, because all I'm doing is adding up numbers there, I'm not really doing anything to try to really bump up the values of the numbers. So they may not be big enough to really spread it nicely across the table. So one issue with this is it produces small integer values. Now, it's heavily dependent now on a couple of different things. But most certainly, it's just, they're not big enough. I want them to, so that these values are really, really big so I could get it all the way down to the bottom of the table. And if it needs to get wrapped around or something using that compression map, then it could find a spot in there. The idea is I want to make sure the value's big enough. So I can make sure if there's a location I can get to, it most certainly could reach it in the table. That's one problem with this. The other one is exactly the one pointed out by a lovely, lovely student. So the biggest problem with this one is it ignores order of characters. So as was pointed out, this sum here, there's many different ways I can get a sum to equal some value. One example of this is if I have a word and I permute the same letters that are in that string. And this is something that happens very often when you have, say, digit-based IDs like student numbers. For example, you may have several student IDs that all have the same number of 1s in them or number of 2s in them. Or just the thing is, if I permute those in my string, it doesn't make any difference. They're going to hash to the same thing, right? That's a problem. At least from the standpoint of the hash code, it will just give us the same output. It will give us the same integer value. That's a problem. Because when the compression map comes along to map it to a position, they'll all go to the same exact position. And if that happens very often, that's going to be a big problem. So ignores orders of characters. Just to give you an example of what I mean. So stop. So if I give you a string, stop. Pots. Tops. and spot all have the same value. So all of these words, they all have some form of meaning to us, right? And that leads to, indeed, as pointed out, more collisions. And that's a problem. so these are kind of two things that really kind of put a death nail into this idea. Now, you can always do it. I encourage you to try it to see for yourself. But I want to show you a second, better attempt at this. It's going to be a little bit more complicated, but I assure you it's a very slick technique that you can also compute in a very natural way, just like the one I have over there on the right. It's just a little bit more. So I'm going to give you my second or suggested approach. So this is one practical way you can compute the hash function. And this one will address the fundamental problem that was exposed, the positions of the symbols. The fact that our hash code is completely oblivious to this leaves us completely open. So remember, so just to clarify, why are we using strings for the hash code? Because remember, in a dictionary, it's very possible that the IDs or keys may actually be strings. For example, like our student IDs, those actually might be strings, for example. So remember, it takes an input. That input is some key. It produces an integer at the end. So the key could be whatever type that's necessary. So it could be an integer, it could be a string, could be an array, could be whatever type you like. So here's our second better attempt that I'm going to recommend. So this one's rather practical. It's very easy to deploy. It is something called a polynomial hash code. We will use a polynomial hash code. So like I said, the main motivation behind us trying this approach is that we want something that isn't oblivious to the fact that all those ways I could permute the letters, they all yield the same value, right? So I want some way to address that issue, and I also want to address the issue of the values not being big enough. So I want to address both of these together, and this approach is going to address both of those. Now, I can't necessarily guarantee, like was pointed out, that I can't have two strings that sum up to the same value. That I still can't eliminate. That is still a potential for a collision. But if I'm able to design effectively this hash code, which this one works rather well in practice, this might be sufficient for practical purposes. So I'm going to, just to make this easier for us, I'm just going to define let the string S be just like I had over there. I'm going to index backwards through the string where I have C sub k minus 1, C k minus 2, all the way down C1, C0. Each character can be converted to an integer, right? So we know how to do that. Now, this is where things are going to get a little bit fun. Because at first, you might look at this and say, this seems rather strange. But I'm hoping that I'll be able to convince you that this type of hash code will address both the problems that we had. At least the ones I drew on over there. So we're going to use these. So I'm going to use the characters as coefficients of a polynomial. So at first this is going to look a little daunting, but I assure you that when you actually implement it, it's just simply a for loop. So at first, just when you look at it, you're like, oh, Dan's really laying on the mayonnaise really tight today. Don't worry, it's really not that complicated. Just don't let it look spooky. It's rather straightforward. So here's what the polynomial is going to look like. So it takes in a string s. So this is what the hash code looks like. So it's going to cast each one of the characters as a coefficient. And it's going to be taken with a value x raised to the exponent. Starting at k minus 1, we're going to go all the way down to 0. So I'm going to cast each one of the characters into an integer. And then I'm going to multiply it by some value x, which I'm going to tell you what might be an ideal choice for that, raised to some exponent here. And you add up all of these. C1, x to the 1. And then lastly, we just have to cast the last one, which that'll be x to the 0, which is just 1. So this is the polynomial that I'm asking you that, like, if I compute the hash code, this is what we're computing. So it looks a little daunting at first, but I assure you it's actually not bad. Now, the natural question is, Dan, you put these x's here. What are those? So this is be a value that you would consider, practically speaking, this is something that you would figure out from a practical standpoint. So you would tinker around with values of x that make most effectively for your hash table. So I'm going to tell you some good examples of values you can use for x, that these are ones that if I go back to the recommended textbook or the optional textbook, the one by Goodrich and all, they give these as suggested values. These are based on computer experiments using, I think it's dictionary words. So I'm going to just cite them. So according to Goodrich et al., and I can vouch, these are pretty good values. Goodrich et al., 33, 37, 39, 41 are all good choices for x. So if you just plug this number in, you can actually compute this for any one string. Yes, that's right. So I'll tell you what the experiment they did was. So just for dramatic purposes, I'm just going to like hold it like this. Just be like, okay. So I'll read it for verbatim just to make it more dramatic. So this was, of course, these are all experimental, just to be very clear. This was done using a list of over 50,000 English words formed as a union of word lists provided in 2 variants of Unix. And they produced fewer than 7 collisions. And one thing I'll point out, because I know of this, is that if you're ever curious about what values some programming languages use, if you ever want to use hashing in that programming language, I think, if my memory serves me correctly, I noted it here, is that, for example, in Java, I know Java, for example, they have a hash code function for their strings. Just as an example. So I'll say Java's hash code, just as an example, uses 31, which is quite similar to these numbers here. But yeah, so here's some examples of practical numbers you can use for the value x. So now the question becomes, how do I compute this? How do I compute this effectively? So that's what I'm going to focus on. And depending on how far along we get, we might start talking about collision resolutions. If not, we'll start that next time. So let's back up and try to figure out what to do with this. First, I gave you this hash code. So this is the definition of the hash code. I haven't yet addressed the compression map. Now, the compression map is often a very simple thing, just to be very clear. Often we use modular arithmetic or mod to often wrap around whatever the number is back into the table's positions. So, just as an example, let me put it together with the hash code to show you what the hash function for this case would look like. So to compute the polynomial hash code, we use a variant. That means just just a slight alteration of another idea. You may have seen this before if you've ever taken a scientific computing class. This is a technique that's very effective for computing polynomials. It's actually based on a very nice grouping trick you could do with polynomials. We use a variant of Horner's method. So for computing polynomials, Horner's method is a rather popular one to use. So I'm going to show you how this hash function would be placed together with Horner's method. So the hash function need to give numbers from 0 to capital M minus 1. So we use the following compression map. So I'm going to write the compression map on the other board, although I much would prefer using the length of this board. Actually, let me write it here. I'm going to write it down here. It's going to span this whole board. I like to show it to you just because it's very nice and dramatic, and I hope I can illustrate a neat idea that within Horner's method. So H, where I give you the string S, is going to be the following. So I'm going to take the compression map together with the hash code. So I'm going to take in, so this is me, I'm defining the hash function. So I give you the string, and what I'm going to do is I'm going to group the terms a little bit differently than you might expect at first. So in Horner's method, what we do is we start at the leftmost side, and we know that we're going to have to multiply the first coefficient by x, then we're going to have to add something, which will be the next coefficient's value, right? Now, for simplicity, I'm going to remove the int conversions just because this gets really long to write otherwise. Now, you know that if I want to compute, I know that this is going to get multiplied by x, right? Just like that is also going to get multiplied by x. Now, I know there's a certain number of these x's that have to get multiplied eventually to the first term here, and the second term, and the third, and the fourth. So this is actually a very clever way of rewriting the same exact computations I wrote up here, but I'm going to make one slight alteration to it by applying the compression map. So I have C3, and then I would have it multiplied by x. And I would keep doing this process of grouping the operations like this. All the way until I get to C2. And I multiply that by x plus C1 times x plus C0 like this. Now, the fun of this is counting how many open and verse close parentheses I have. I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Let's see. 1, 2, 3, 4. Let's see. 1, 2, 3, 4. 1, 2, 3, 4. We'll go with this. So if you're not convinced that this is actually equal to this, I encourage you to try it with a smaller polynomial, and you'll see that you can actually expand what I have at the bottom here into this. But by writing it out like this, we could actually reduce the number of multiplications that actually happen by half, roughly, which is quite nice from a performance standpoint. So I have this. Now I need to make sure that this is some number between 0 and m minus 1, so I apply the compression map, which in this case, all it is just I apply mod m. So this will make it so it's a number between 0 and m minus 1. So this is just getting the integer remainder. And this is actually what the hash function would look like for computing the polynomial hash code. So there's actually one serious practical consideration if I had computed this directly. Now, does anybody remember, you may have seen this, maybe in first year. Has anybody ever heard of the, remember, this produces inside of here. There might be a really big number that gets computed. It's going to be some integer. Are there going to be any problems with us having a really, really big integer in here? Is there any technical issues we have to worry about? It might be too big, exactly. It might be way out of the range of possible values that the type integer can take on. Now, obviously, if you know it's only going to be a certain size, then obviously you could declare a variable, but I would like to have some way to ensure that this number, if it gets too big, it does not cause what we know as integer overflow, right? So, you may know of this concept. It's called integer overflow. So this is what happens when the integers get too big, integer overflow. So what happens, especially if they're signed or unsigned, they can cause very interesting behavior for your computer programs if the number ends up being too big. It might turn into a negative number. I encourage you to try this on a computer sometime. It's just try to make an integer that's just like the maximum size. And if it's an integer that allows negative numbers, if you try adding 1 or some number value off of it, you'll see if it flips to some sporadic number you wouldn't even predict. Or you could predict it if you understood integer overflow. But my point is that we have issues with finite sized numbers on computers, especially if we're using int, okay? So I'm going to give you a very simple way of resolving this issue. It's all based on the properties of modular arithmetic. So it's worth noting that whenever I compute one of these groupings of products, a product with a sum, each one of these has a nice property, and this follows from the same principles that I used to put this in a position from 0 to m minus 1. Each one of these, if I compute it, so it's mod m in between each one of these parentheses, when I carry this out, it'll keep it as a number between 0 and m minus 1 every single time after I do this product. So it'll bring it down every time. So when it starts getting up a little bit bigger, it'll put it back to a number between 0 and n minus 1, and keep applying this over and over again so the number doesn't get way too big. Just big enough that it will give us a number between 0 and m minus 1. So I'm going to show you how I'm going to achieve this. So let me just head over here. So let's head over there. I'm going to give you the pseudocode for Horner's method. And inside of there, I'll show you exactly how we resolve this. And this is all entirely based on the properties of modular arithmetic. So if you're ever curious about that, you may learn a bit more about that if you haven't already. And if you find yourself curious about it, I know sometimes, I can't remember if it's taught in 310, but I know most certainly if you're curious more about these kind of properties, any kind of number theory background might get you the background for this kind of thing. It's really a neat thing. Essentially, addition and products with modular arithmetic tend to get preserved over the over modulus or the modular arithmetic operators like mod. So that's something we're going to be using. So just to recap what I said about the issue, in intermediate computations, there's possibility of integer overflow. This is not an issue. So all we're going to do is we're going to apply mod, which if you're not familiar with the mod operator, it's % in C++. So you may have seen it in that context. For each iteration of Horner's method. So I'm going to now present you our modified version of Horner's method. If you want to make it Horner's method, you just get rid of the mod, okay? So here we go. I'm going to call it hash function because this is the one that I'm recommending, but you don't have to use this one. So here's the hash function. So I'm going to call the algorithm, I'm going to call it hash function. It takes in a string s and a value x. Remember, this is something that you decide. And so you get to pick what x is. So this would be something like the values I had suggested. So remember, as input, it takes in a string s, which is ck minus 1, ck minus 2, all the way down to c1, c0, and a value x. And as output, it's going to give us a position in the table. So position for s in the hash table of size m. So capital M. So keep in mind that this would be some number you decide prior to the decision of building the table. So here we go. I'm going to assign val to be the integer casted version of the last character. And then now you might say, Dan, we only have like a couple minutes now. This algorithm is very simple. So watch this, watch this. This is why I also recommend it when you're computing polynomials. So for I is assigned k minus 2. We're going to go down to, so this is just me saying you're going to have a for loop. You're going to start at value k minus 2, and you're going to decrement instead of incrementing down to 0. We're going to do the following. So all I'm going to do is I'm going to assign val to be whatever val times x plus int of ci is where I apply mod. So I go mod m on that. And then I'm just, after this, all I'm going to do is return val mod capital M. And that's it. That's it. So you can use this if you get rid of the mod operators there. This is actually Horner's method. This is one way you can write it. Now, one neat thing that I should point out for you before we leave, I'll leave the analysis for you to think about. It's in the notes, but I want to point out, because I want to let you go, is that if k is a constant, the hash function is computed in constant time, big O of 1 time. So just to take a quick look at this, look at how many iterations this for loop has, and that should tell you everything you need to know. So notice that the running time depends on k here. So that being said, I'm going to stop right here. I want to say thank you very much, and have yourself a beautiful day. When we come back, we'll talk more about hashing. We'll talk about collision resolutions. I'll see you later.